All right, so last time we had started with this Jacobi iterative solver, part of the discussion on iterative solvers. Is someone saying something? Please mute your microphones to avoid feedback, unless you want to say something. So the discussion on the Jacobi iterative solver was the beginning discussion on the general idea of iterative solvers. And we had said that the iterative solvers are amazing and much better for sparse systems of equations. Those are systems that once you write in matrix form, they have mostly zeros everywhere. 50% or more of the answers are actually zero in that matrix. And the idea of the iterative solver is based on an analogy with the equations with a single variable, such as this one, ax equal b. If you were to solve for x, you would simply just solve that equation for x, which is b over a. And last time we said, okay, what if we extend this thought and consider, for example, this system of two equations with two unknowns, the unknowns here being x1, x2 for lack of another variable name, and then say, okay, let's solve equation 1 for x1. So essentially invert the first equation for x1. Now, don't worry about x2 on the right-hand side. Don't worry about that. We'll think about that in a minute. And solve equation 2 for x2. However, you know, as you can see, we need values for x1 and x2. It's kind of a circular argument over here. However, since we're doing numerical methods and since we're gonna iterate over the system, why not start with a guess for x1 and x2 and consider the numbers on the left side, on the left-hand side, the x1 and the x2 on the left-hand side as the update of the guesses for x1 and x2. And so starting with an initial guess at 0, let's say not the value 0, but a counter. So the 0th guess, the first guess we have, we call it x1, 0, x2, 0. That's not a power. That's just a counter. Okay. Then you would say my new x1 is equal 1 over a11, b1 minus a12, x2, x2, 0. And the same thing with x2 using the previous values. All right. Now this equation becomes a recipe for an update or a correction for your initial guess. Remember, the idea of iterative methods is we start with a guess and we develop a recipe to improve that guess to get hopefully closer to a solution. And this recipe here is telling us just use the original system of equations, put in whatever knowledge you have, whatever guesses you have on the right-hand side, and just deduce an updated value on the left-hand side. And essentially, that allows us to put a counter on each one of those variables. So notice on the right-hand side, I have the counter 0 for x1, x2. So that's using previous information, the guess in this case. And the updated values are have a superscript 1. Again, this is not a power. Okay, this is just a counter k. We're going to call it k in a minute. And just essentially rinse and repeat. Now take these new updated values, x11 and x21, and put them again on the right-hand side and develop and update your formula. So you get x12 and x22 using the most recent values, x11 and x21, and so on and so forth. You can continue this. So there's a typo here. I mentioned that last time. Let me actually, I cannot fix it right now because I don't have the equation editor that I was using, but I'll update that on the slides. So this third equation should be on the right-hand side, should be x22 and x12, and so on until you just have this general formula for the k+1 estimate for the solution is a function of the kth estimate of the solution. And as you can see it here, x1k plus 1, etc., is equal to something as a function of x2k, x1k, and so on. And I had given you this, I had shown this simple example over here just for this system of 2x2 equations. And you can run the numbers by hand. It's kind of tends to become tedious, but anyway, this one is two equations with two unknowns, x1, x2. The exact solution is 0.4 and 2.7. and start taking the Jacobi method, starting with an initial guess at 0, 0. We just take, for example, here, the first iteration puts us at 2.5 and 2.8. And then you can take those 2.5, 2.8, put them again in the right-hand side, and you get 0.4, 2.3, and you keep iterating. And after 100 iterations, in this case, you get 0.47 and 2.7, 2.71, and which is almost identical to the exact solution. Okay. Now, clearly, this was an example to illustrate the idea. I used two equations and two unknowns. We need to generalize this. So I'm going to go ahead and extend this example to a system of 3 equations with 3 unknowns. Okay. So we're going to write it this way as our 3 equations with the standard coefficients for the matrix, the Aij indexing. This should be clear to you. These are just 3 equations, 3 unknowns, the unknowns being x1, x2, and x3. And we apply the same idea. We say solve equation 1 for x1, equation 2 for x2, and equation 3 for x3. So we're really kind of going over the diagonal terms. And you see how this looks like. X1, k plus 1. The k plus 1 estimate for x1 is equal something 1 over a11 times b1, etc., etc. But all a function of all in terms of the kth iterate. So starting with an initial guess, this would be the 0th iterate, you get the first one, and then you start using the first one, you get the second one, and so on and so forth. Okay. That's my son here. Okay. And then and so now I want to make a small adjustment over here to make this more amenable or easier to program. Because if you want to go and program this, we're not going to program it 1 entry at a time, or at least for the Jacobi method. I'm gonna try to write this whenever I have the opportunity to write this in terms of a vector matrix multiplication. I want to take that opportunity. So if you focus on the first equation here for x1, you notice on the right-hand side you have a12 x2 to the k, x2 kth iterate, not to the k, and a13 x3 k. And if you look at the matrix, that's almost like the dot product of the first row in the matrix and the column vector x1, x2, x3, but it's missing a11 x1. Okay. It's missing a11 x1. So what I'm going to do, I'm going to add and subtract a11 x1 and write it in this form. So notice I'm going to move the slide back and forth. What I did here, I simply added a11 x1 and I subtracted it, a11 x1 k, so that on the right I have a full matrix row dot product with the guess, and equal the k plus 1 iteration is on the left hand side. And so I simply added a11 x1. So this is x1k, and over here you have minus 1 over a11 xk. And same thing over here, I added and subtracted a22 x2k, x2k, and same over here, I added and subtracted x3k. The reason I do this is so that this, whatever is on the right hand side, is actually going to be the dot product between one of the rows of the matrix and the vector of solution guesses. Okay. All right, so with that, now you get the general formula for the Jacobi method, and which is for a general system of equations with n unknowns. Okay, it doesn't have to be 2, it doesn't have to be 3, it could be 50, it could be 1,000. Okay, the solution for the ith variable xi, the k plus 1 iteration for the ith variable is equal the kth iteration for the ith variable plus 1 over aii, that's the entry in the matrix, times bi minus this summation over here is actually that dot product that I referred to. Give me a second. Okay, now another simpler form which we might use, but this only applies to the Jacobi method, unfortunately, is this fully vectorized form, which is way simpler than having to write a for loop. We're going to adopt a for loop. So this form that I have, this first equation, you have to do it as a for loop. as you will see when I show you the code. Whereas the form below, you can do it just as a vector multiplication, vector matrix multiplication in Python, but that only applies to the Jacobi method. The form that I'm showing that requires a for loop in this first equation will allow us to just simply extend this to the next method we're going to talk about, which is the Gauss-Seidel method. Okay. Here's in summary what the Jacobi algorithm entails. So now you understand what I wanted you to take from this is a basic understanding of how the Jacobi method works. You solve the ith equation for the ith unknown, and you keep iterating on that. Okay, so for equation 1, you solve the first equation for the first unknown, equation 2, solve the second equation for the second unknown, and so on and so forth, using previous values that existed, starting with an initial guess. What this would entail, you always need an initial guess because you got to start from somewhere. That xi0, you got to start from somewhere and then update your guess for each of the unknowns that you're solving for until you get to a fixed number of iteration count. Say you want to do 50 iterations, so that would put k at 49, right? Or you would want to put 1,000 iterations, or we're gonna choose a stopping criterion a little bit later. Now, I've shown you the code here, and I'll share it with you in a Jupyter notebook in a minute, and I'll give it to you also in the homework assignment. So you don't have to worry about what goes on in the code, but just kind of roughly going through it. I'm defining a Jacobi subroutine, define Jacobi, and that subroutine takes a coefficient matrix A, takes a vector x guess, takes a vector of right-hand sides, and takes a maximum number of iterations. Now, why do I need to pass it a matrix A? Because the Jacobi method is not specific for the Jacobi method is not specific for tridiagonal matrices. Remember, the Thomas algorithm only applied to tridiagonal matrices, right? So all you needed to give it were the three three diagonals, main diagonal, first upper, and first lower diagonal, right? But for Jacobi method, this applies to general sparse matrices, right? And that being said, you gotta give it the full matrix. Now, there are ways to give that full matrix in an efficient way, so you don't have to store all the zeros. We leave that discussion for a later time. But for now, you gotta give it a full matrix, okay? You gotta give the full matrix, needs to be a full matrix, so we can loop through it. It needs a vector of x guesses. How many x guesses do you need? As many as there are unknowns in the problem you're solving. If you have 3 unknowns and 3 equations, you gotta give 3 initial guesses. If you have 100 unknowns, you gotta give it 100 initial guesses. Okay. B is the right-hand side. It's going to be the same size of the number of unknowns. And maximum iterations over here, right now with our current structure of the Jacobi subroutine, is a maximum number of iterations. So that's how many iterations we are going to take. And now inside the subroutine, you are welcome to study it. First, I take my A matrix and I convert it to a NumPy array, because generally so far, we have only passed lists as arrays, right? But I need to turn it into a NumPy array so that I can use some cool NumPy features, okay? So whether this is a NumPy array or not, doesn't matter, because this line over here converts it to a NumPy array. Just a little, nuance over here. Next, I'm grabbing the number of rows and number of columns. And here you can make sure, you can, for example, do error checking. You can check whether the number of rows equals to the number of columns to make sure that this system is invertible, right? I don't do that over here, but I need this number of rows or number of columns just to know how many unknowns I have. I could grab that from the number of entries in XGuess. It's up to you. Then I set an iteration counter to 0. And I initialize my solution array. I call it X. In the notebook I'll share with you, I call it sol, doesn't matter. And I initialize it to zeros. Okay, so this is kind of just an empty array full of zeros that I'm gonna fill out with a solution. Give me a minute, my voice one. Sorry, my son was singing and he's gotten really into it. So I told him to use his inner voice while he's singing. And then finally, we start our iterative loop. In this case, I'm doing a while loop, which is, a conditional for loop. As long as my number of iterations is less than the maximum iterations, then do the thing, do your thing, Mr. Jacobi algorithm. And that is, for now I'm going to go and loop over each equation, right? So that's what if you remember, the Jacobi formula said, xi k plus 1 is equal to xi plus something, right? So that's exactly what I'm going to do over here. Okay. Oh, sorry about this. Let me go back to this. Okay. So for the ice iterate, so I'm going to loop over each and every equation. I'm going to loop over each and every equation and start do my x guess over here. I'm starting with my x guess and plus 1 over aii times bi minus ai times x guess. So that's the dot product. Sorry, my son is making me laugh over here. Okay, I apologize about that again. So this is the formula, and then finally we update our x guess. We make a copy of our updated solution. If you don't make a copy over here, it's gonna keep changing the memory for xi. So you better make a copy. So now you've updated your x guess to the new values, right? And then you can reuse it next time, and so on and so forth. Anyway, you're welcome to dissect how this code is working. We're not going to do it together here. We're just going to use it. This is an example for one system with 3 equations and 3 unknowns. We're going to do this together in a coding activity. If you grab the LinSolve activity 5, Jacobi with gaps from the linear solvers module on Canvas, and we'll be able to do this together. Okay. All right, everyone with me here? Was the audio, everything looking okay? All right, thank you. Apologies about my son really likes to sing and like play with his dinosaurs, and so I had an agreement with him that he would, if he wants to see me teach the class, which I really like, I would love to even actually bring him to class for him, to be exposed to these things. But yeah. I apologize about that. All right, so
that is adorable.
Hey, thank you, Trayton. I appreciate it. Again, I don't mean for this to be unprofessional, but it's kind of the thing. We're all quarantined here, and like, he can't go back to his school for like 10 days now. So, so Tata is saying he can teach us about dinosaurs. Well, if we have some extra time, I'll have him come and talk about some of his hypotheses. He's been learning about hypothesis testing now, and the dinosaurs. So, but maybe on Thursday, if we have some extra time when we wrap up the iterative solvers, I'll have them do that. But all right, let's open up Jupyter notebooks, please, and I will share this one. Let me see. I should have my Jupyter notebook open over here. Go ahead and open it. Apparently, I don't have it over here. So local host. So I'm going to have to share this individual window right now in 450. So the notebook doesn't have any gaps for the first example. It's going to have some gaps for the for when we go to Gauss-Seidel. Okay, so you're welcome to just kind of go and start playing around with some of the numbers until I get this one open over here. Solvers activities. All right, that will be the gaps. Okay. I'm going to try to share this individual window over here with you. Okay, can you see my my shared window? Perfect. Thank you. Okay. All right, so we're starting with this system: 5x1 plus x2 plus x3 equal 10, 2x1 plus 3x2 equal 11, and 3x1 plus 4x3 equal 12. It is diagonally dominant. I set it up this way. And I have the boilerplate over here already for you, import NumPy, etc. And that little tip I gave you last time about using scalable vector graphics. And finally, I have this additional little thing over here, NumPy dot set print options, and I'm setting it to a precision of 5. So essentially, it's just going to show about just 5 digits. You know, it's not really significant figures. It doesn't know that. It's just showing up to 5 decimal points. Okay. So you go ahead and execute that, and I have the Jacobi method over here, Jacobi subroutine implemented. Notice I changed X to solution. So go ahead and execute that one, and then finally here define your coefficient matrix. Right-hand side, initial guess and maximum iterations. Apparently, I did put some gaps over here for you. So this is the coefficient matrix. Excuse me, 5, 1, 1, 2, 3, 0, and 3, 0, 4. With the right-hand side, 10, 11, 12. And for your initial guess, you know, put whatever you want. I'm going to put 0, 0, and 0. Okay. And that sets our initial guess. And now simply call the Jacobi solver. What I'm going to do over here, I'm going to call Jacobi. And again, Jacobi takes coefficient matrix, right-hand side, initial guess, and a maximum number of iterations. You know, we can put, for example, 10 iterations. And if you run it, it's just going to return an answer. Okay, 0.92 and 3.04, etc. Now, to check the exact solution, you can do np.linalgebra.solve, right? And then you can put A and B, and this is the exact solution obtained from a direct solver. Okay, so you notice that the first iteration, we're kind of getting close. First unknown, we're getting close to the solution. Second unknown. Third one, we're almost there as well. Clearly, if you do 50 iterations or more iterations, to be more accurate, you're going to get much closer to the solution. I hope you're all agreeing with this and seeing this right now. Okay. However, you know, it would be nice to get a clearer idea of what's happening inside the iterates. And what I've done here is I said, okay, I want to gain some more insight to what the solver is doing. Okay. And so what I want to do, I want to print out, okay, each iterate. All right. And I already did this here for you. And I actually want to go ahead and plot the solution for each iterate as a function of iterations, because as you will see, if you go ahead and execute this this cell over here, so execute it and then run the one below it, if you notice, after a certain number of iterations, the numbers for each unknown, so 0.93, 0.23, etc., they don't change much anymore, or at least they're changing at higher decimal points. So if I change my precision NumPy print out precision to 10, okay, and go ahead and execute this again, okay, notice the change is actually just happening at very high significant figures or very high decimal points. Okay, and so, you know, this seems to be like almost inefficient, right? Because I would probably have stopped just over here at iteration 16 and said, you know what, my computer or this algorithm is not doing any better anymore. It's sort of just hovering and trying to improve the last, you know, the 5th or the 7th decimal point, and I really don't care about that. And so to prove this to you, what you can do, you can go ahead and plot the iterates, okay? And I've done that for you over here. So if you go and execute this cell, so let me maybe zoom in if you can't see me very well, so you see this very well. If you plot the iterations as the solution or how we're converging to the solution, you notice that, you know, within 10 iterations, we're not improving much. Initially, we start with an initial guess. And so this is the first iterative. We start with initial guess all at 0, and then we're kind of far apart, and then we improve a lot right? We oscillate and then we quickly gravitate and converge to the correct answer. You're welcome to change your initial guesses and see what happens. So if you go over here and put x0 and say change it to 15, 30, and then 11, okay, run it again, and then we print this again. You notice there's a significant change happening over here. Don't mind this, what's happening over here. This is due to round off. But if you look, we quickly converge after 10 iterations. We quickly converge to an answer. Okay, we quickly converge to an answer. Okay, I don't know what's going on here. I'll look it up a little bit, but look at that. It's actually just converging very, very quickly to an answer. So it seems to be wildly inefficient to actually spend time trying to converge the system beyond what it can do, okay? Beyond what it can actually do. So let me share the slides again with you, and then we can pick it up from there. First share the screen. Okay. And now, okay. So this is exactly what I have on this slide. That very slow change, very little change in the solution occurs in this case for this problem. Okay, this is not the general rule for this problem. The general rule is many of these systems with Jacobi, you get to converge. Your solution doesn't change much after a few iterations, and so it seems wildly inefficient to continue iterating to infinity, right? So how do you choose your number of iterations? Clearly, this is going to be dependent on the initial guess that you've taken and how fast you get to that point where you're not changing, where your numbers are not changing much. It also depends on the coefficient matrix and on the right-hand side. And so passing on a maximum number of iterations seems like a bad idea to get a solution. So we need a better way to tell the solver when to stop the iterations. And we call this convergence. When do you stop iterating? Okay, so I'm gonna share this with you now, this block, and I'm gonna ask you a question. Take a moment and consider when should we stop iterating? Feel free to just jump in or raise your hand. Just come up with a thought. No, remember the plot? Initially, there was a lot of change, but then there was not much change anymore, right?
Would you want to stop after you reach a specified amount of significant figures?
Of significant figures? Yeah, but how do you tell? Yeah, that's the right thinking, but how do we tell that? So how can you turn that into math? So what Rich said is correct. What he's saying is after the iterates, okay, or the number of it, so consider the slides again. So at iteration 10 and iteration, let's say, the one after it is iteration 11, for example, there's not much change in the first four decimal points, right? Or,
would it be like your relative approximate error?
Yes, thank you, Rich. You nailed it, right? So this is a great example of critical thinking. First, you think of the thought intuitively, like, what do we want to do? And then you may turn it into math. So to follow up on what Rich said, Rich is saying, look, after a certain number of iterations, the numbers, the first decimal points look the same, right? So what if we take the difference between these two and let's just say, once you hit the same number of significant figures, the same number of decimal points, I want to call them, in your solution, once you hit the same number of decimal points in your solution, stop iterating, okay? And that would be an approximate relative error, right? The k+1 iteration minus the kth iteration, okay? the k plus 1 iteration minus the kth iteration over the k plus 1 iteration if you want a relative error, and say stop over there, right? So this is exactly what we're looking for. Okay, but there's still a hiccup over here. Okay, so this is exactly what I have here, the relative approximate error. So what I'm gonna do here, I'm gonna create a table for each iteration. Okay, for each iteration, I'm gonna compute the approximate relative error. So that's k plus current iteration minus previous iteration over current iteration. Okay, and I'm gonna take the absolute value and declare that to be an error. The problem though is that you have, for each solution variable, you have its own error, right? So in this case, we have 3 solution variables, the unknowns, x1, x2, x3, and therefore you're gonna have 3 errors, E1, E2, and E3. So for iteration 1, E1 is 10 to the minus 1, E2 is 6, 10 to the minus 1, and then E3 is 5, 10 to the minus 1. For iteration 30, you have 3 errors. So which one do you pick? Okay, which one would you pick? Again, I'm passing the floor on to you. So it seems like you can take the worst case scenario, right? So that would be, for example, here for iteration 30, if you're looking at the slides, you know what? 10 to the minus, we met 7 significant figures, 7 decimal points, right? So, and we hold the solution, the convergence accountable to that one. Okay, we always say, oh, we haven't converged. So we're taking the maximum of all of those 3 errors. And that's legitimate. Okay, but there's a more kind of general way of thinking about this. Can you think of a way of thinking about it?
I would say something like the sum of the errors, just add them together.
But adding them, you're compounding the effect. What if you take the average, right? So you can take that average, for example, correct? Right, so what other thoughts could be? What if you think, so now I have a table, right, rows and columns, etc. What if you forget about this table and just pick one iteration line? So let's take iteration 10 and consider those 3 numbers, okay, in this case 3 numbers only, as a vector of 3 components. What's a measure of the size of a vector? Now, that was asked of you in equation in exam 1. Ethan, you wanted to say something?
I guess so. I guess we're just going to use the magnitude of the vector then?
Yes, precisely.
Okay.
Yes. So what Ethan is saying is, look, we can use the maximum, the maximum error, the worst case scenario, or we can take the average, like Trayton said, or we can take the magnitude. So that's the Pythagorean norm, right? All of those are valid ways of holding this accountable to an error norm. The right word over here is to say we need an aggregate measure of our error. What this aggregate measure is usually doesn't matter as long as it takes into consideration all of the errors involved. Remember, you might have 100,000 of these errors at a given iteration, okay? So you need to take their aggregate value, okay? You need to take their aggregate value all together. And this is what I'm showing here on this slide. So together, E1, E2, and E3 form a vector at each iteration. And that collective measure, I'm gonna call it vector norms, which you have studied. And some of the vector norms that we consider is the L1 norm, which is essentially either the average or just taking the sum, like Trayton said, or the magnitude, like Ethan said, or the L infinity norm, which is the maximum, the worst case scenario, like I had suggested in the beginning. So take the worst error and say, until that worst error satisfies 10 decimal points, keep iterating, okay? And you can do this numerically in Python by calling the NumPy linear algebra module called norm. Just one moment. Okay, there was some singing going on. I don't know if you heard it, but it was extremely noisy over here. So these norms, you take a vector A And when you call norm A1, that gives you the L1 norm. Norm A2 gives you the L2 norm, which is the Pythagorean average. And the NP dot infinity gives you the L infinity norm. Okay. And then, excuse me, for each iteration, we can simply compute a norm of the error, an aggregate measure of all of these errors. I want one number. And that number, I'm going to hold it accountable to how many decimal points I need in my solution. Okay, and it works so well. And then we stop when the norm reaches that desired number of decimal points. We call it tolerance. That's our tolerance. So we say our tolerance is 10 to the minus 4. I want, 4 decimal points, 4 significant figures if you want in my error, and then I'm gonna call it a day. Okay. And so if you take this same example and you compute the norm, look at that. So you had 3 errors at each iteration, but with the L2 norm computed on those iterations, it gives you just a single number, and you can make sense from that single number. So that single number could be, you could have 100,000 unknowns, right? But you'll have still one single number, and you could say, as long as that single number, as long as my aggregate error is less than 10 to the minus 5, I'm good to go. We're going to stop iterating. So now that gives you a better way to think about your iterative solver, okay, without having to pass a very, very large number, of iterations. Now, we will discuss later that it would be wise to also pass a maximum number of iterations, just in case you could never reach that tolerance, okay? But you typically put like 10,000, for example, or 500, right? And some number, the problem you might be solving, you may be more familiar with. So problems in fluid mechanics, generally our iterative solvers should converge within 50 iterations, 100 tops. But some problems are so exotic that, playing around with them, I realized that I need 300 iterations here. So I put my maximum iterations at like 350, 300, and I put a tolerance, okay? And I put a desired tolerance, the one that I want. Now, which norm do you choose? Whichever one you like, as long as you are clear and non-ambiguous about it, okay? So you can say, I want an L2 norm, I want an L1 norm, an infinity norm, doesn't matter. It really doesn't matter. It's just a measure of the aggregate, but as long as you are clear to the user as to which norm you are using. Now you can pass this as an option to the solution subroutine. I wouldn't do that. Okay, it's not necessary because that requires expert knowledge in what the subroutine is doing, whereas the subroutine should just solve a linear system of equations up to a desired tolerance. Okay, shouldn't be the responsibility of the user to know what error norm you're using. Okay, now Rich mentioned we use the approximate relative error, right? So we take k plus 1 iteration iterate minus the previous iterate over the current iterate, okay? So current minus previous over current. But that's only one measure of an error. And that is typically the one I personally like, because that tells me how well this subroutine is gonna do for a given problem. Because once the iterates cannot change anymore, that's the best the algorithm is gonna do. Okay, but there are other measures as well that you can use to calculate the error. Okay, so do you want to take a moment and think about one? So clearly we don't have to do a relative error. We can do just the approximate error, xk plus 1 minus xk. Okay, because what if your xk plus 1 is 0 and you have a 0 in the denominator? It might mess things up. So you don't have to do a relative one. You can just do an absolute one, xk plus 1 minus xk. So, but what other error can you think of to see if your solution is good, how well your solution solves the system of equations? Think about it. You have ax equal b, you know a, you know b. You're trying to find x, right? And I'm asking you, as you're trying to find x, how can you tell that this x is a solution to the system of equations? How can you tell that the solution is a solution to the system of equations?
Just plug in the X value to the equation, see if it solves.
Yes, thank you, Rich. Okay, so we're gonna tell Rich not to take answers, not to give answers anymore, because he's taken a lot of answers correctly too. And so yes, Rich is correct. What he's saying is that as we compute our improved guesses, our improved solution, the simplest thing you can do is take that solution and plug it into the system of equations, right? So you have ax equal b. So if you take a value for x and plug it in, how close is it to b? Or in other words, ax minus b, how close is it to 0? And that gives you a sort of a measure of a true error, if you think about it, which is crazy, right? That's pretty cool, okay? So some of the other error measures is actually just take b minus ax to the power k, and they take the norm of that, okay? So b is your right-hand side vector, ax to the k is your coefficient matrix times your current solution, okay? And that's a vector. So b minus ax k is a vector, and you can take its norm. So you can use that as an absolute measure of the error, okay? That's actually a sort of a true error, okay? It's a sort of a true error because you're looking at the real system you're solving, okay? And so that's one measure of the error. The other one was the approximate error. And if you have the exact solution, clearly you can take with the, you can take the difference with the exact solution. That's kind of obvious. Or you can take a relative version of those errors. So either, you know, use a true error, b minus ax, and see how close you are to 0, or take the approximate error xk minus 1, or current minus previous, or take the relative versions of those errors, okay? Now, the relative version is important because ax equal b doesn't necessarily have to be very close to 0. It depends on the scale of the system you're dealing with. If you're dealing with temperatures on the order of 500, 600 kelvins, right, an error in 1 Kelvin is not a big deal, correct? But if you're dealing in a system, you're solving a system where, you know, you're looking at pressure differences that are on the order, you know, of 0.1 and 10 to the minus 4, etc., then an error of 10 to the minus 4 is a big deal, right? So you need a smaller error. So then you would take the relative error, for example, in that case, you do the ax minus b over bi. My personal preference, always, I don't care which one you choose, okay? As long as you are clear about it. And when you're using a third-party solver, understand what they mean, what their stopping criteria are. I personally am a big fan of the approximate error, the absolute approximate error, xk plus 1 minus xk, because it just tells me this is the best that this solver is capable of doing, okay? But this is my personal choice, okay? So how you would do this then? So this is only gives you the mechanism of how you compute the error. So you compute the error in your for loop, in your while loop, and then you would stop once your user-defined tolerance has been reached. So once your epsilon, once your error measure is less than or equal to the tolerance, and then you would stop, okay? Then you would stop. Clearly, when you're writing an iterative solver, just be clear to tell the user whether to expect a relative or absolute tolerance, because this is going to be an argument that we're going to pass to the iterative solver. And you're going to do that right now. Go back to your LinSolve Jupyter notebook, the Jacobi one, and let's scroll down to one of the cells at the bottom and discuss how we're going to implement this error measure, okay? Okay. Excuse me. So now here I kept this all of these printouts. So I'm printing out the iteration, the solution, and the error as well. But I want you to spend a minute to fill in the gaps over here. So this is the same Jacobi algorithm we had before. What I changed here is instead of maximum iterations, I passed on a tolerance, okay, a tolerance value in the argument. So the user would give A, the coefficient matrix, the right-hand side, the initial guess, and the tolerance, okay? And you start computing things, but I want to introduce an error over here. Okay, I want to introduce an error measure. So go ahead and spend a few minutes to try to introduce an error measure. Clearly, before we enter the while loop, we need to get an idea of what our error is. Okay, and then in the while loop, when do you stop? So error should be when do you stop that conditional for loop or the while loop? Error should be less than the tolerance or something. And then how do you update your error measure as you seek out your solution? Okay. Anyone have any idea? Let's start with the error over here. We're going into the Jacobi algorithm. We need to put in an error. Okay. We need to put in an error here, an error measure. What do you think? Zih. What are you thinking about the error? Anyone have any idea?
Like for that highlighted spot?
Yes. Sorry, I didn't hear you.
Plug in your guess.
Is that the error?
Oh, sorry. So like B minus your guess plugged into A.
Okay, so how do we do that? Right. Right, that's A. Remember last time I said you can take the dot product between a matrix and a vector. We're using this add symbol, A add B. If this is not working, there's another version, MP dot, and you can put A and X guess. Okay, so that's kind of our initial error, right? We can't do anything better than that. Or you can put a large value to force it to go into the iteration. Okay, so you can put, you know, whatever, 100,000 over here or so, or a million, right? But, you know, we can do this, but this is not enough because this is a vector, right? So you need to add mp.linalgebra.norm, okay? And we're gonna take an L2 norm, okay? Okay, now what about the while loop? What about the while loop?
I mean, wouldn't it just be as long as it's greater than our tolerance?
Correct. Yes, as long as the error is greater than the tolerance, keep going. All right, thank you, Ethan. Let's see if someone else can contribute. All right, error here, over here. So now we need to update that error, right? So we came in probably with a very large error. Now, as we start improving our solution, we need to start estimating how we're changing that error. So what would you put here? Clearly, it's going to be a norm. So mp.lin algebra.norm of something, right? I'm going to do a second norm. So what if I want to do the relative, not the relative, just the approximate error? So xk plus 1 minus xk. What would you suggest we do for xk plus 1 minus xk? So my current solution is solved. My current xk plus 1 iteration is solved. So I'm going to put solve, okay, right? What is my previous solution is going to be x guess. right? That's it. That's all there is. So put this in, hoping it works. And then let's run Jacobi 3, give it a b x0, this initial guess, and 10 to the minus 2 tolerance. Look at that. It ran, what, 14 iterations, and it gave us stopped at an error at the tolerance of 10 to the minus 2. Okay. You want more? Go to 10 to the minus 4. It went up to 21 iterations. Okay. Right? You change your initial guess, it's going to change. All of that is going to change. Okay. All of that is going to change. So play around with this. You're welcome to try now to do the other iteration, the other error measure. Okay. If you do error, so you do the other measure, which is the same as this one, b minus a dot b minus a dot x, but you do it on the solution, okay, on the most recent value, and you take a L2 norm or an infinity norm. They're all going to be almost identical. Okay, they might add one more iteration or two more iterations. That's not a very big deal. Okay, that's not a big deal. Okay. So let's take a 3-minute break, please. Let's just take a 3-minute break, and I'll come and see you in 3 minutes. Okay, play around with this. I'll see you in 3 minutes. Saw some messages on the chat. I apologize. When I'm recording and sharing the screen, I don't see anything in the chat. I'm sorry for those of you who were trying to contribute to answers. I know Paula and Bark D and Nicholas have been sharing some answers. It's impossible for me to see the chat while I'm sharing a screen and kind of trying to manage all of this. So please, if you're okay, just kind of speak up or raise your hand or remind me that there's something in the chat, but I cannot see the chat while I'm sharing the screen. Anyway, so now we can get back to the slides, and let me share the other screen. Okay. Share the other screen. All right. So we're done with this kind of survey on the errors. Now, again, what's helpful is to think about this intuitively. Like, what are you doing in each one of those errors? Okay. The reason I like the approximate error is that it tells you just this is the best you can do on this computer with this problem, and regardless of whether you're solving the actual system or not. And that to me is decent enough. Okay. Now here on the slides, I'm sharing with you these two algorithms. The first one, these two implementations, which I will share with you in a Python file. Okay. Don't have to worry about those. Okay. Excuse me. Now on to one of our better iterative solvers, and that's called the Gauss-Seidel iterative solver. Now, if you notice in the Jacobi iteration, notice that when we said we solved equation 1 for x1, equation 2 for the second unknown, equation 3 for the third unknown, everything that went on the right was using the old values, okay, was using the initial guess. So take the example we did with the 3 equations and 3 unknowns. X1 only required x2 0 and x3 0. But now you updated x1. When you go to x2 in Jacobi, x2 was a function of x1 0 and x3 0. But you have an updated value for x1. You just solved for it. So why not use that? Why not use the most recent information? So in other words, just a simple manipulation of the Jacobi method, where you see here on the right-hand side, you're always using previous old information. Why don't you use the most recent information available? If you are doing x4 and you had x1, x2, and x3 over here, use the most recent ones, okay? Just use the most recent ones that you just updated. So I convert this, the math is a little bit more complicated than what I've written here, but I write it as use the most recent. You see xj recent. Always use the most recent information that you have. Don't use the old information only. Use the most recent information you have. If you have an x1 that you just computed, use it. If you have an x2, just use it. Use the most recent information. And that tends in general to cut the number of iterations, surprisingly, for many, many problems by half, okay? So again, I give this kind of little example over here. You can do it by hand, but the best thing is to do in Python, actually, over in this case. But for this example that we were just doing, Gauss-Seidel requires about half the number of iterations of Jacobi to achieve the same tolerance, okay? Now I want to show you this, and let's do it in a Jupyter notebook. There's another notebook in the modules, the activity 6, Gauss-Seidel with gaps, okay? So I want you to go ahead and open that, load it up, and let's get our hands messing with it, okay? Linear algebra, LinSolve activity 6, Gauss-Seidel with gaps, okay? So let me open this on my end. All right, can you see my my screen? Perfect, thanks. Okay, so again, kind of importing the same standard boilerplate, and I have this initial, this general Jacobi that takes a tolerance, okay? So here we're headed out to try to prove and show how we can implement the Gauss-Seidel and try to prove that it's a little bit faster than Jacobi, okay? So you go ahead, execute Jacobi. This is just kind of standard stuff we've done in the previous notebook. Declare the coefficient matrix, declare the right-hand side. Over here, I'm putting an initial guess of 1, could be 0, whatever you want. And for some reason, I specified a maximum number of iterations, okay? Now, I'm gonna take the Jacobi algorithm. Like I said in the slide, the Jacobi algorithm is simply, the Gauss-Seidel algorithm is simply a modification of the Jacobi. So I copied and pasted the Jacobi algorithm over here, and I changed the name to Gauss-Seidel. Still takes coefficient matrix, right-hand side, initial guess, and a tolerance. But the Gauss-Seidel uses the most recent information available, okay? So now pay attention. Over here, xi, notice, xi was using xold and xold, this guy over here, ai dot xold. Okay, so that's the dot product of the ith row of the matrix and the old solution vector. With Gauss-Seidel, we said we're going to use the most recent information. So go ahead, think about that for a moment, and let me know what you think should go in there. So this is doing the solution for the ith equation, okay? We want to use the most recent information. as it goes through each row, it's updating. So think about xi over here. Xi contains our solution, okay? It contains our solution and it's self-updating, okay? So for the I equation, we solve for the ith unknown and we just kind of update in the spot. So you go through the first equation, you update the first solution. You go to the second equation, you already have an updated solution for x1, okay? For x2, you want to use that most recent value. So what are you going to do over here? What are you going to use, x old or the most, how do you use the most recent information? Okay, I might have someone in the chat. Okay, so I opened the chat window. It's easier for me if you guys would just speak up, please. Okay, so I have Paula saying xi, and Nicholas is saying just x. Okay, so you're on the right track, but is this sufficient if I put xi?
Wouldn't it be AI dot X?
Correct. Yes, you need a dot x, right? So you need that a dot x. Okay, you need that a dot x over there. So what I would do, I would take the ith row, so it would be a I. Okay, actually the add is not going to work. Dot x, and you don't need xi because x is in the entire solution vector. So what this has the effect of doing, because x is being updated as you go, okay, this would pick up the most recent values that you've computed, okay, and that you've filled in inside of x. Okay, now imagine this used to be a homework assignment in the past. I would ask students to write the Gauss-Seidel algorithm. This was one of the steps that always kind of got everyone entangled. And so I think it's better now to just share the code with you and kind of work together through it. Okay, so now let's go ahead and compare the behavior. I'm choosing a tolerance of 10 to the minus 5. I want the Jacobi solution, I call Jacobi, and I want the Gauss-Seidel solution, I call Gauss-Seidel, okay? So let's run those. For 10 to the minus 5, notice the Jacobi solution took about 21 iterations, okay? And the Gauss to reach a tolerance of 10 to the minus 5, and the Gauss-Seidel took about 9 iterations, okay? This is pretty amazing. This is pretty awesome. Just a simple change of using the most updated value led to this huge difference in calculation. Now, this is a big deal for methods that are repetitively solving linear systems. So for example, in fluid dynamic simulations, for a transient calculation that's time dependent, every time, every step in the solution phase, I'm solving a linear system of equations. So if I can cut my number of iterations by half, I've cut 1 month of simulation time, probably by a week or so, you know, or even more, because number of iterations is not the only thing that matters in that case, right? So it's a big deal, right? It is really a big deal having these kind of these improvements. Okay. All right, so I have one more improvement before I let you go, and I think I can cover it in 5 minutes, I hope. COVID is weird because sometimes you feel energetic and then like a minute later you're like, oh, I don't feel well at all. So all right, let's see, let me share the screen again, and this will be really kind of the end of our iterative solver discussion. The last solver I want to talk about is called successive over relaxation. Think of iterative methods as a technique, a recipe taking you from the kth solution vector, the kth iterate, xk, to xk plus 1. Now, x is a vector containing all the solution, right? The solution entries, x1, x2, x3, and so on. Temperature, T1, T2, T3, etc., right? It's a vector. And so the distance or the direction from xk to xk plus 1, that's generally the direction of the solution that your solution is taking, right? You can declare this as a vector in n-dimensional space, okay? So think of this as moving in the direction of the vector r, which is xk plus 1 minus xk. Okay, so technically that's the difference between our updated solution and our old gas and our updated gas. But it's actually, if visually, it is a direction that your solution recipe is taking to achieve a solution. Now, this recipe is actually a formula. So for Jacobi, it's simply this formula. For Gauss-Seidel, it's that other formula, right? You see the most recent here. So it's simply xk minus 1, xk plus 1 minus xk. That's a direction, okay? That's sort of a direction vector. Now, one might ask, then, you could say that xk plus 1 is xk plus r, which is a tautological calculation, a tautological thing. However, the power of the symbol here, assume that R is just a recipe. Could be Jacobi, could be Gauss-Seidel, could be something you invented, tomorrow or whatever. It's just a recipe. It's the direction that it's the direction of the true solution. Now you might say, okay, well, if we know the direction of the solution, why not go faster or slower direction? And what you do, you simply say, take that direction, which is R, that recipe for Gauss-Seidel and Jacobi, and multiply it by a number so that you move faster in that direction or you move slower in that direction. And this is called simply successive over relaxation. And by introducing this parameter omega that multiplies the direction in which you are moving to get to the solution, or also known as the recipe for your solution, you can either increase your convergence rate or slow it down if you don't want to converge too fast. W, omega, is called a relaxation parameter. So you either over relax if you are greater than 1, or under relax if you are less than 1. Omega is a positive, should be a positive value. And typically for our recipe, for our direction vector, we always use the Gauss-Seidel because it is faster than Jacobi. It's a no-brainer, sort of, right? In general, you can prove that omega needs to be between 0 and 2. Anything above 2, your solution is going to blow up very fast. But that's the slight modification you can do. So you can go back to the notebook and just add a relaxation parameter, okay, and see how your solution changes. Let's see, we have like half a minute to try to do this. I'll do it with you, and then I let you go. Okay, let me share my window. Okay, I'm gonna go back to the Gauss-Seidel, and I'm gonna add a relaxation parameter. Okay, I'm gonna put a W over here, and I simply have to put W over here. Okay, so when I do this, and I'm gonna go to Gauss-Seidel, I'm gonna add a W, let's say 1.5. Okay. Now, okay, it's still at 9 iterations, okay? If I do 0.1, now the Gauss-Seidel solution is not having any effect. For this problem, it is not having any effect. For some problems, it has a huge effect, okay? Typically, this effect will be seen, so sorry, that was kind of let down. I'll come up with a problem where this omega we see it more in heat transfer and fluid mechanics all the time. And there's usually like an optimum value for this omega to get like the best, the fastest convergence. But sometimes you can screw things up really bad if you choose the wrong omega. So it's a double-edged sword. However, it allows you to control your convergence rate of the solution just by simply adding a factor, this constant value. Yes. All right. So with that, I'll end the lecture. Yes. So let's yeah. Mike, who was talking? Michael? Oh, sorry. Someone was saying something.
Is it all right if I asked you if we could look at where you used omega in your code again?
Oh, yes. I'm sorry. Just omega 1 over AII. Just put omega instead of 1. So it's omega over AII.
Oh, I understand.
Okay?
That makes sense.
Yeah. Let me share that code again. Who was talking? Sorry,
Ethan.
Ethan. Yes, Ethan. Okay, so Ethan, right over here, omega over AII. See, it used to be 1.0. You turn it into omega?
Awesome. Thank you.
Yeah. All right. Thank you, guys. I will see you on Thursday. hopefully, if my case doesn't get worse.